morning, everyone. Welcome to our lecture on improper integrals. Can you confirm that you can hear me? Um, is it faint? What's the problem, James? My volume is low. Okay, let me try to see if I can do something about it. Okay, is it better now? Um, I'm not sure what to do here. All right, I'll try and shout. Okay, so we are looking at improper integrals, and what we want is to be able to integrate certain functions. Um, so what we have been dealing with at the moment was to integrate functions that are defined on some closed and bounded interval like that, right? And now what we want is to be able to solve, to integrate some functions such that um, instead of having a value there, we've got infinity. And instead of having a closed and bounded function like this, we might have some discontinuities on our function. Okay, so the volume is still low. Let me try and put a different set of headsets. Maybe it might help. Okay, I've put a different set of headsets, or a different set of headsets. I hope that helps. I'm not sure where the volume is low, but just confirm what is now happening. Um, is it still low? Oh, okay, it's better. Okay, thank you. I hope it's better for everyone. So I was saying the function that we are dealing with is closed. We were dealing with closed and bounded functions, and now we want to look at something a bit different. So just as a motivation, suppose you want to see what happens when you integrate this function, which is starting from 1 and it goes to infinity. And you realize that if we're to draw it, so just assume that this is your y is equal to 1 over x squared, and then you want to integrate. So if we think about, if we say, suppose a t is the integral from 1 to t of 1 over x squared dx, where t is greater or equal to 1, um, then what we want is to then see what happens when we look, for example, at a 100 and a 10 to the 5. So you realize that for the first one, a to the 100, let me use something a bit faint. We are going to have this as our um, integral. And then if we look at something, this is not really proportionate, but just to illustrate what we are trying to say, then you would realize that we now have this as our integral. So you see that as t becomes bigger, the integral that we are adding, or the area that we are adding, becomes smaller, and you'd actually realize that as we get bigger, we are getting closer to the actual integral, right? So if we continue like that, then we are getting closer to 1. And so here we don't really know if it's 1 or not. I'm just illustrating. We'll prove that the integral is actually equal to 1. But the point is, as we get closer to infinity, what we are adding becomes smaller and smaller. In other words, the integral becomes, the value of the integral becomes 1. So he says when the headsets were plugged out, the audio was great. Okay. All right. Let me put them out. Just let me know if it's better now, so that I can continue like this. Right. So we've got this, and oh, okay. All right. Thank you for that. All right. So now I know what to do. Okay. All right. So we've got these integrals, and they get closer to 1. And so let's look at this from a general point of view. Right. So we've got what are called improper integrals of type 1. And you realize that so we've got 2 types. I mentioned that one is when the set is not closed and bounded. Well, in both cases, the set will not be closed and bounded. But what changes is, in this case, instead of having a b there, we've got infinity. That is type 1. Or instead of having an a, we've got minus infinity. That is part of type 1. And then we'll talk about discontinuities within the interval that we are given. That will be type 2, maybe tomorrow or late in the lecture. Right. So our type 1, to put it more formally, if you've got a function f that is defined on this set, so from a to infinity, and the integral from a to t exists for every t that is greater than, let me use red, for every t that is greater or equal to 1, then what it means is the integral from 0 to infinity is actually just the limit as t tends to infinity of this is supposed to be a there, a from a to t of f of x dx. So you integrate with respect to t, well, with the upper bound being t, and then you take the limit, and then you find out what the integral is. So if that limit exists, right, and is a real number, then we then say that the improper integral is convergent, right? So take note that there are two conditions that needs to be met. Number 1, the limit exists. Number 2, it is a real number for us to call it a convergent integral, right? And then the same applies. So instead of having here we're saying, instead of having AB, we've got this. Now again, instead of having that, so the B here is the A, and then the A becomes minus infinity. So we are just doing the corresponding definition for minus infinity. So if f is defined on this, and if we look at this, it always exists for any t that is less than or equal to a, then the integral from minus infinity to a, here not infinity, a of f of x dx is the limit as t tends to minus infinity of this, right? So again, we create this function and then we take the limit as t goes to minus infinity, and again, if the limit exists and is a real number, then we then say the function or the integral is convergent, right? So as I mentioned, in both cases we want the limit to exist and the limit to be a real number for us to say that um, the integral is convergent, right? So if it doesn't exist, so we've got two possibilities of the opposite of this. Either it doesn't exist, or it's going to exist but not a real number, right? So these are two possibilities that might happen, and in that case we then say the integral is divergent, right? So if one of these doesn't one of these, if the opposite of what we have here happens, then we say the integral is divergent, right? So just to put it more formally, so let a be a real number and f be a continuous on this set, such that this integral exists for all t greater than a, greater or equal to a. Then what we call this integral is just the limit as f of t, the limit as t tends to infinity of f of t. And if that is not convergent, so if the integral is not convergent, then it is divergent. And for us to say it's divergent, we are going to have two cases. Either the limit exists and it's equal to plus or minus infinity, or the limit doesn't even exist, and that's when we say the function is divergent, right? And what we have said here, all of this also applies to the case where we've got the integral from minus infinity to a, right? So all the statements, you just change where there's a infinity, you put minus a, minus infinity a, right? To get the same statements for minus infinity. So let's look at some examples to see how this goes. So we will start off with the function that we had at the top. So for example, we want to prove that the integral from 1 to infinity of 1 over x squared dx is equal to 1, right? So let's see how that goes. So if we say this 1 over x squared dx is going to be the by the definition that we've just had, it's just going to be the limit as t tends to infinity of the integral from 1 to t of 1 over x squared dx, right? And then from there, we know that the integral of 1 over x squared always exists, so that is a good thing. So we then say this is going to be the integral. If we integrate 1 over x squared, we get 1 over x from 1 to t, right? The bounds are there, and then we can then say the limit as t tends to infinity, and then we evaluate what we get there. So if we put our t, we get minus 1 over t, and then if we put 1, we get minus 1 over 1, like that, right? And this just becomes the limit as t tends to infinity of 1 minus 1 over t, and this is equal to 1. And we have shown that our integral is equal to 1. So there is a question or there's a comment which says, you lost me. I am not sure what you mean by that. Maybe um, maybe you can elaborate. So how did we get to the second step? Are you talking about from moving here to there or from there to there? So if I call this star, well, from moving left to there, star, and then this star, star, which one do you mean? Here we just use the definition that we have been given in type 1 improper integrals, and then from there we just integrated 1 over x squared. So 1 over x squared, that will be x to the minus 2. If you add 1 and then divide, you end up with this, if I'm not mistaken. Otherwise, it should be a routine. Okay, all right, great. You are happy. All right, so that's how we do that. So therefore, we can say that's number 1. This converges, the integral converges, and its value is 1, right? And the value is 1. Right, let's look at a slightly different example. So suppose you are given this integral. So we want to prove that this integral is convergent, and once we do that, then we find the value. Find the value of the integral, right? Right, so the integral there is going to be equal to, by our definition, the limit as t tends to infinity of the integral from 0 to t of s squared e to the minus s ds, like that, right? So we want to find this, but maybe we should break it down so that we know what we are doing. This integral, we need to use integration by parts. I think you can see that. Otherwise, it will be a bit tricky. So let's say the integral from the indefinite integral is equal to s squared e minus e to the minus s ds. And then once we find the indefinite integral, then we can find the definite integral. And then once we find that, we then take the limit, and then we have our answer. I hope that is clear. So the 3 steps: indefinite integral, then we deal with the definite integral, and then we then take the limit. Right, so we'll say let f of s be equal to s squared, and f prime of s would be equal to 2s, and let g prime of s used to x s. So we are saying let this happen, which is minus s, and g of s, we integrate that, we get minus e to the minus s. Right, and then we use our integration by parts, so we get s squared times minus e minus to the minus s minus the integral of 2s times minus e to the minus s ds, like that, right? We just used our formula for integration by parts, and then we get minus s squared minus e to the minus s plus the integral of 2s e to the minus s. I just took out the minus there, and then we got a plus there, right? And then we still need to deal with this integral. So we say let ps, or whatever letter you prefer, and be 2s, and then q prime of s be equal to minus e plus e to the minus s. So that is our ps, that is our q prime s. And then so if we differentiate, we get that is equal to 2, and then if we integrate that, we get minus e to the minus s. And then again we use our integration by parts. So I'm not going to do this separately, I'm just going to do it combined. So I start by that minus s squared e to the minus s, plus we do the integration by parts of that. So 2s times e to the minus s minus 2 that times that, so 2 times minus e to the minus s ds. And then we get minus s squared e to the minus s plus, so we can put minus here because we've got a minus there, minus s minus 2s e to the minus s, and then plus 2 times e to the minus s ds, right? Which is that we just take the minus outside and then we get a positive, and then we get that minus e to the minus s minus 2s e to the minus s, plus now we just integrate this function. So if we integrate it, we get minus 2e to the minus s, and then plus a constant. Don't forget the constant, because here we are dealing with an indefinite integral. Now we get on to the definite integral. So now we've got an indefinite integral, so we can say the limit as t tends to infinity of the integral from 0 to t of s squared e to the minus s ds is going to be equal to the limit as t tends to infinity of what we got inside there, so minus s squared e to the minus s minus 2s minus e to the minus s minus 2 e to the minus s, like that. And then we put our bounds there, right? And then from there we can then evaluate for 0 and t, and then we get minus t squared e to the minus s minus 2t e to the minus sorry, not minus s but minus t, since we are putting t there, t, and then minus 2 e to the minus t. And then when we evaluate for 0, that becomes 0, that becomes 0, so we are left with that. So e to the 0 is just 1, so we end up with minus 2, like that. And then we can then say this is the limit as t tends to infinity of minus t squared e to the minus t minus 2t e to the minus t minus 2 e to the minus t plus 2, right? And now we want to find out what's the limit. So before we go to the answer, we will realize that, well, we need to find out what these are. This one, as t tends to infinity, should be easy. So so the limit as t tends to infinity of 2 over e to the minus t, I want to deal with this one first. It is just going to be equal to sorry, not minus t but to the t there. So if t is going to infinity, this becomes bigger and bigger, so we are going to 0, right? And then let's look at t, the next one, which is that one. So this would be 2t e to the minus t, which is the limit as t tends to infinity of 2t over e to the t, right? And if we look at that, that's the numerator goes to infinity, the denominator goes to infinity, so we've got an infinity over infinity case. So we can apply L'Hopital. I'll just write it in shorthand there, right? Because it's in that form. And then we then say the limit as t tends to infinity. And then we differentiate the top part, we get 2. We differentiate the bottom part, we get e to the t. And now we've got a constant on the top, and then on the bottom we've got something going to infinity, so it's like we'll have like a 2 over infinity type. And once we get that, we know that this is going to be equal to 0. Let's look at the next function, which is the first one there. So if we write it, so we get t squared e to the minus t over, sorry, there's no over here, and that can be written as the limit as t tends to infinity of t squared over e to the t, right? And then we can see t squared as t tends to infinity, t squared goes to infinity, and e to the t goes to infinity, so we've got an infinity over infinity situation. So we can use L'Hopital, and so therefore we can say this would be equal to that, and then we differentiate the top part, we get 2t, we differentiate the bottom part, we get that. And as t tends to infinity, again 2t is going to infinity, and e to the t is also going to infinity, so we still have the situation like that. So we can use L'Hopital again, and we get the limit as t tends to infinity. We differentiate 2t, we get 2. We differentiate e to the t, we get e to the t, and then we've gotten 2 over infinity situation, and we know that that is going to 0. So in other words, here this goes to 0, that goes to 0, and that goes to 0, right? So therefore we can then say the limit as t tends to infinity, all those go to 0 of 2, which is equal to 2. And so therefore we can then conclude here, we can conclude that this improper integral is convergent, because we saw that the integral exists and it converges, and it's equal to 2, right, which is a real number. So therefore we can say, and the value is 2, like that. Right, so that's how we do this. Let's look at our next example, and it's going to give us another way, another criteria to find out if integrals are convergent or divergent in some cases. So let I be equal to the integral from 1 up to infinity of 1 over x to the p dx, right? And the question is, for which p is I going to be convergent? So that is the question there. Right, so let's look at some cases. We will subdivide it into cases and see what happens. So case 1, suppose that p is equal to 1, right? Then what it means is I would be equal to the integral from 1 to infinity of 1 over x dx, and the limit as t tends to infinity from 1 to t would be like that, 1 over x dx. We are just using the definition here, and then we know how to integrate 1 over x, so we get the limit as t tends to infinity of the natural log of x, right? And then we put our bounds there. And then from there we then say, we evaluate, and we get this is the natural log of t minus the natural log of 1. And that becomes the limit as t tends to infinity. If we evaluate, we know the natural log of 1 is 0, so we end up with the natural log of t, which is going to be equal to infinity. And so therefore we can say the integral diverges in this case. Right. So this is a situation where, so just to show you something that might happen, the limit is okay, the limit as x tends to infinity of f of x can go to 0, but the integral from 1 to infinity of f of x dx is infinity. So this is a classical example of having a function such that its limit goes to infinity. Sorry, as x tends to infinity is equal to 0, but when you integrate, you find out that the integral is actually infinity. You would intuitively most likely think that if the limit of a function is as x tends to infinity is equal to 0, you would expect the integral to be convergent. But in this case, we can see that that is not the case. Right. Let's go to the next case, and we are going to look when case 2, when p is greater than 1. What happens? Then we've got I is going to be equal to the integral is going to be from 1 to infinity of 1 over x to the p dx, which is going to be, there's a question, let me just see. So for this type of question, is the best method to solve it by trial and error? Not quite. We are going to actually have a test which we call the p-test for this type of questions. I'm just showing you why it's true, but you can just quote the statement which tell you about the p-test. I hope that clears that part. Right. So we've got that, and then if we can rewrite this as 1 to infinity of 1 over x to the minus p dx, and this is going to be the limit as t tends to infinity of the integral from 1 to t of x to the minus p dx, right? And so we want to integrate x to the minus p, and we know that the integral is just x to the 1 over x to the 1 minus p over 1 minus p. So you add 1 on the on the power, and then you divide by that new power. We know that how to do that. Where one and then we evaluate from 1 to p. And remember, in this case, we can do this, so we can divide by this value because p is not equal to 1. So there's no problem there. We are not going to get something over 0 there. And then we say limit as t tends to infinity. If we evaluate, we get t to the 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. Sorry, not p minus 1, 1 minus p. Like that. And then this is going to be the limit as t tends to infinity of t to the 1 minus p over 1 minus p plus, so if you look at the numerator there, it's just 1. And you can rewrite this as p minus 1. If you take out a minus on the bottom and then you reconcile with that minus, you get a positive there. Right, and then we know that the limit as t tends to infinity, so we've got two functions, or the limit of a sum of two functions there. So the last one, we know because there's no t involved, we can say that that is 1 over p minus 1. And then the other one, the limit as t tends to infinity of t to the 1 minus p over 1 minus p. And in this case, if you look at 1 minus p, okay, so this value, because p is greater than 1, so since p is greater than 1, it means that 1 minus p is less than 0. And so if you think about the limit as t tends to infinity of t to the 1 minus p, it will be something, because this value is less than 0, it will be at the bottom. So if you then take the power t, some power, if you take t which is going to infinity, then you would have 1 over infinity, which becomes 0. So that value becomes 0. So there's a question, why does it become p minus 1? So I explained that, so the top part there will be equal to 1. 1 to the power anything is equal to 1. And then 1 minus p can be written as minus p minus 1. And then if you take this minus that we took out there and then this minus, then we get a plus. So we end up with that. It's not really necessary, you can leave it as that. I just wanted to have positive values here, but otherwise it's not necessary. I hope that clears that. Right. So there is another question. Please explain the last part. I'm assuming you're talking about this part. Okay, so since p is greater than 1, we know 1 minus p is less than 0, right? Here. And then now if you look at this, so basically what we are going to have is something like the limit is, we can rewrite this statement as 1 over t to the p minus 1, where we know p minus 1 is a positive value. I hope that is clear. And once it becomes positive and this one is getting bigger, then we are going to have a situation of 1 over infinity, which becomes 0. I hope that is fine. So we are saying p is greater than 1, so it means p minus 1 is greater than 0. But remember that we are saying this is 1 over p, so we would have said t to the minus p minus 1 like that, right? And we know the p minus 1 is positive, so we can say this is 1 over t to the p minus 1, where p minus 1 is positive, and so therefore whatever we have there is going to positive infinity, so 1 over infinity becomes 0. So that's where the 0 is coming from, and I hope that clears that question. Right, so therefore we've got 0 and we've got p minus 1 there. Thus, if p is greater than 1, then the improper integral converges to 1 over p minus 1 plus 0, which is equal to 1 over p minus 1. And in actual fact, we did this question for p is equal to 2. So we did p is equal to 2 earlier if you recall, when we looked at the integral from 0 to it was from 1, from the integral from 1 to infinity of 1 over x squared dx. So that was just a special case of this case that we are dealing with, where p is greater than 1. Now let's look at the last case, right? So we know, of course, that if you've got a value p, it's either greater than 1, it's equal to 1, or is less than 1, right? We know this. So we now deal with the last case. We've dealt with that and that for now. So we look at case 3 where p is less than 1. So if p is less than 1, then the integral from 1 to infinity of 1 over x to the p dx is equal to the limit as t tends to infinity of the integral from 1 to t of x to the minus p dx, right? Again, we do the same integration that we did as in the last case, in the previous case. Then we get that 1 to t, and then we end up with the limit as t tends to infinity of t to the 1 minus p over 1 minus p plus 1 over p minus 1, right? We just did what we did in the last one. So now we want to see what the limits are in this case where p is less than 1. So we know the last one is easy because there is no t involved. So p minus 1 becomes 1 over p minus 1. But if we look at the limit as t tends to infinity of t to the 1 minus p over 1 minus p, we will see this is going to infinity. And the reason is, if p is less than 1, then 1 minus p is greater than 0. It's a positive value. And so if you think about the limit as t tends to infinity, then so we've got t to the 1 minus p, which is, we know that this value is positive, right? 1 minus p is positive, and we are saying this number is becoming larger, so t is going to infinity. So t going to infinity to the power some positive value will give us infinity, right? So we get that is equal to that, and this is just a constant, so it's not going to affect whatever limit we get. If the limit is going to infinity, so it will be like an infinity over p over some constant which is infinity. So we get that, and so in this case we can see the limit exists, but it is not a real number. So this improper integral diverges. And then so what it means is, our answer is the integral from 1 to infinity of 1 over x to the p dx is going to converge. So this converges if and only if p is greater than 1, from what we saw in our 3 cases. When p is equal to 1, we saw that the limit is infinity. When p is greater than 1, we saw that our limit is 1 over p minus 1. And then, sorry, not here. Okay, so it was here where we saw that this becomes 1 over p minus 1. And then in this case, the last one, we saw that it's going to infinity. So the only case where it's going to converge is when p is greater than 1. And this is what is called the p-test. So the answer is what is called the p-test. If you've got a function such that you say 1 over x to some p, you just need to check if p is greater than 1 for you to know if it converges or not. So there's a question. So when we talk about p less than 1, we assume just less than 1. I'm not sure what you mean. Maybe you can elaborate. But otherwise, what we are saying is we are not, well, we are definitely not assuming that p is equal to 1 because we dealt with that in a separate case. What we want is when p is less than 1 and that we make our argument there. Maybe you can elaborate if it's still not clear what's happening. So this is what we call the p-test, and we are going to look at an example for a p-test. So I was saying that you just need to check if the power is greater than 1 for you to conclude that it's going to be convergent. Otherwise, it's divergent. Right. So let's look at an example. Let k be equal to the integral from 1 to infinity of 1 over x to the p squared minus 8 dx. Right? And the question is, when does this improper integral converge? And we can then say by the p-test, p squared, so we know that the power should be greater than 1 for it to converge, right? So p squared, and in this case, okay, let me use red. Our power is p squared minus 8. So we've got all the other elements. We've got our 1 there, so that's fine. We've got a infinity there, we are fine, and then we've got 1 over x to some power, so that corresponds. But we are saying the power should be, by this rule, the power should be greater than 1, right? So in other words, p squared minus 8 should be greater than 1. And so we want to find out when is p squared minus 8 greater than 1 for us to find out if it's going to be, where it's going to be convergent. So we then say, if we do that, then p squared minus, if we put our 1 on the other side, we get p squared minus 9 is greater than 0. And if we factorize, we get p minus 3, and then p plus 3 greater than 0. And now we want to find out when we are going to have something that is going to be like this. We want to find where the values, these values are positive. So our critical values are is minus 3 and 3 there. And then, so if you take a value between minus 3 and plug it in there, you'll see that it's going to be negative. Take 0, for example. You get minus 3 times 3, which is minus 9, which is negative. And then if you take something bigger than 3, so take 5, for example, you get 5 minus 3, 5 plus 3, so 8 times 2, and then you get a positive value, so you know that that is positive. And then if you take a value that is less than 3, so you pick whatever, minus 3, for example, you get minus for the first one, minus for the second one. If you multiply, you get a positive value. So in other words, this is going to be true in these regions where it's positive, right? We know this is positive, so we want in these regions. So the answer is going to be p when p is from minus infinity to minus 3, and then from 3 to infinity, right? And we don't include the minus 3 and 3 because at this point we are going to get zeros, so that doesn't work. Right, so that will be the solution in this case of finding what what are the values for p such that p squared minus 8, so such that this integral is convergent. Right, now let me come back to the question that Braden is asking. So do we talk about a value uh, do we talk about a value just to the left of 1 like minus 9, or any value less than 1 like minus 10,000? You can pick, so we are talking about p, right? So p, if you can take minus 1,000, minus 10,000 is still fine. It's still the same, because the idea is, so when p is less than 1, let me look at that case. When p is less than 1, if you take 1,000 for example, then where are we? Okay, so for p less than 1, what we are saying is, if you, oh, okay, all right, you are overthinking. All right, don't worry. Well, I wanted to give you an example, but I think it's clear. If you just put your minus 1,000, minus 10,000, then you will see that it will still work, because the argument is the same for any value that is less than 1. So just plug it in the value and see what happens, for you to satisfy yourself. Right, so the answer is this, and we use the p-test here. So we'll continue tomorrow and look at the comparison test, and then we'll look at type 2 improper integrals. Thank you for your time. If you have questions, I will stay for maybe a minute or so. Otherwise, enjoy the rest of your day. Bye. Okay, it seems that there are no questions, so thank you for your time. Enjoy the rest of the day and have a productive week. Bye.